Hello and good evening. My name is Harish, and today I'll be presenting a short video on the thermal efficiency and brake mean effective pressure for a four-stroke internal combustion engine which runs on the Otto cycle. Uh, I'll be using such flashcards over here so that it'll be easier to explain my video as it goes along. So let's start now. So first of all, before we begin, let's have a look at the two types of internal combustion engines. They can be either two-stroke or four-stroke engines. Now, what's the fundamental difference between a two-stroke and four-stroke engine? It's that for a single cycle, a two-stroke engine requires only two strokes, which means that the piston only needs to go once upwards and downwards for the entire cycle to be completed. In comparison, the four-stroke engine needs four strokes for a single cycle to be completed, which means that the piston needs to go upwards twice and downwards twice before one cycle is completed. As you can see, the two-stroke engine can obviously complete a single cycle faster than a four-stroke engine. This means that for a given mass, the two-stroke engine can produce a higher power output. But at the same time, because of its inlet and outlet design, it will be less efficient, which is why a four-stroke engine is normally preferred. Now, now, let's talk about the four-stroke engine because that's what we're concerned about over here. The four-stroke engine can also run on many different cycles. They can be the Otto cycle, the diesel cycle, the Atkinson cycle, Brayton cycle, and so on. Now, since we're only concerned with the Otto cycle, let's have a quick look at what that actual cycle means. As you can see over here, what happens in the Otto cycle is that the compression stroke happens isentropically while the heat is supplied at constant volume. Isentropic expansion then takes place, after which the heat is rejected at constant volume. This means that it can be called a constant volume cycle. Now, let's have a look at the PV and TS diagrams for an Otto cycle so that things will be much clearer. So over here you can see that I've highlighted the first stage, which is the compression stroke in both the PV and TS diagrams over here. Obviously, because it is a compression stroke, you can see that it follows the adiabatic curve over here and it goes from 1 to 2, during which the volume has decreased while the power has increased, and in the same manner the temperature has increased while there has been no change in entropy. This is because this is the isentropic cycle and there is no change in entropy. Now, the next stage that you see over here is one of heat addition. As I said previously, heat addition is done at constant volume, which is why you can see over here that there is no change in volume as the temperature increases, because of which pressure increases. This is because of the gas law, which gives us PV equals nRT, which means that pressure is proportional to, directly proportional to temperature. As you can see, because heat has been added, its temperature has gone up, but because we are plotting pressure versus volume and temperature has gone up, hence pressure can be seen as going up while the volume has been constantly maintained. This is also seen over here in the TS diagram, where the temperature has increased from zero point 0.2 to zero point 0.3. So as we said before, this is what is to be expected, and hopefully you're understanding what's going on over here right now. Now the next stage is one of adiabatic expansion, specifically isentropic expansion, which means that it is a reversible process as well. Over here you can see expansion taking place on the PV diagram, where you can see that the volume has changed from 0.2 to 0.3, and similarly you can see on the TS diagram that because it's an isentropic process, there's been no change in the entropy while the temperature has gone down because volume has decreased. Now the last stages of heat rejection, and as stated before, it takes place at constant volume hence you can see that on the PV diagram the volume has not changed from zero point 0.3 to zero point 0.4. On the TS diagram you can see that the entropy has decreased because you have rejected heat. And one thing think I should point out is this line over here. This has not been covered so far. To show that there is a change in the working fluid, this line denotes that the working fluid has been changed. It goes out and a fresh charge is coming in over here. Now let's move on to our actual discussion, which will be of thermal efficiency. Now, first of all, the basic laws of physics suggest that energy is always to be conserved. Energy is neither created nor lost. So that gives us a very fundamental equation that delta E is always equals to zero, which means that whatever energy you are giving into the system plus whatever energy you're taking out of the system must always equate to zero. This can be expanded as follows, which gives you that the work done from in the process 1 to 2 plus the heat added in process 2 to 3 plus the work done in 3 to 4 plus the heat rejected in 4 to 1 always equates to 0. Now you can calculate the efficiency, which is the work done divided by the heat supplied to it, which is given over here. This is the thermal efficiency for any cycle, for any object, for any process that you consider. So this is always its standard form, and as you can see over here, the total net work done will be W1 to 2 plus W3 to 4, and because you're only supplying heat in the process 2 to 3, it will be divided by Q2 to 3. So that gives you eta equals W1 to 2 plus W2 to 3 over Q2 to 3. Now let's expand on our thermal efficiency formula some more. You can see that we can rewrite our standard equations that I showed you just now in terms of internal energies as well. Internal energy is the sum of energy which is possessed by any object at its current state. It can be it is included of chemical energy, mechanical energy, thermal energy. Everything is included when we talk about internal energy. So now, as you can see over here, we have rewritten W1 to 2, W2 to 3 in terms of internal energy, which is essentially the work done is defined as the change in internal energy. Because as I said before, you can neither create nor destroy energy, it only changes form, which means that when you're doing work, you have supplied some of your internal energy in another form, and then you've come down to a different level of internal energy. I said before that heat is always added or rejected at constant volume, which means that the heat constants can be defined as heat constant at constant pressure and at constant volume, which are Cp and Cv, as you obviously know. Cp over Cv is gamma, and Cp minus Cv is the gas constant R. So after knowing that, you can write eta in terms of Cp and Cv, but we will only write it in terms of Cv because we only have constant volume processes involved in the Otto cycle. Now, one thing we haven't considered so far and explained are the compression ratios and pressure ratios and so on. So that is something that I'll be trying to cover quickly. As you saw in the previous diagrams, like over here, you can see that the volume has actually gone down. So this V1 over V4 can actually be expressed as V1 over V4 or V4 over V1, and this ratio is termed as compression or expansion ratio. Obviously, because this is a constant volume cycle, the compression and expansion ratios remain the same, but in diesel cycles and other cycles, we'll be having compression and expansion ratios differently because they take place as different processes. So over here, let's try to turn these things in terms of compression ratio because that remains constant for a single cycle. Not for a single cycle actually, but for any given engine. Compression ratios are fixed because it depends on the stroke and the clearance volume of your engine for your cylinder and so on. So you can treat it as a constant for a given engine. So rewriting your equations in those terms is quite helpful. So let's carry on. As you can see over here, the temperature ratio can the ratio of temperatures can obviously be written in terms of a ratio of volumes, and because it is an adiabatic process, you also have your gamma involved over here. Because you have V1 over V2 given over here, this can be treated as a compression ratio. uh, Hence you can put it back up in this equation over here, and your thermal efficiency is 1 minus 1 over your compression ratio to the power gamma minus 1. Now let's have a look at the final topic in our discussion today. It will be mean effective pressure for the Otto cycle. Now mean effective pressure is given as the work done divided by the stroke volume. This gives you a pressure mean because as I showed it to you in the previous PV diagrams, you can see that the pressure is constantly changing. If you have a look over here, you can see that the pressure drops as compression or expansion occurs, which is okay, but for quick calculations and so on, if you have your mean effective pressure, calculating work done becomes uh, quite simple because all you have to do is multiply your mean effective pressure by your stroke volume, and you'll get your work done, which is what uh, is the standard equation for simple processes, which is given as work done equals P delta V. So to derive the same thing, we have tried to come up with a new quantity which is given as P mean effective pressure. As you can see over here, your mean effective pressure can be your stroke volume is given as the total cylinder volume divided by the clearance volume. This is because there's a clearance volume, a small amount left at the top of every cylinder, which allows for the smooth operation of the intake and exhaust valves. Since this clearance volume can never be zero, so this is one thing that always comes in when you try to calculate your stroke volume. Uh, Previously, I talked about the compression ratio, but now it's time to bring in a new constant known as the pressure ratio. So you can see that pressure can obviously be written in terms of volume as well, or more specifically, the ratio of pressures can be written in terms of ratio of volumes. Obviously, there will be the involvement of gamma here as well because P1 and because you have the isentropic equation of PV to the power gamma is constant. So you can write your pressure ratios in terms of your compression ratios as well. So that becomes somewhat easy when you're trying to calculate the efficiency as well as the work done for a given cycle. So we'll have a look at this final chart over here, which is just equations. So we'll try to go over these equations one by one so that it becomes more clear to everyone. Since work done for an isentropic process is given as P1 V1 minus P2 V2 over gamma minus 1. We have tried to expand on that over here. Uh, Obviously, because work is being done in one cycle as positive and in the other as negative. But since work is obviously being done as either positive or negative, you have to consider both cases over here. So the net work done will be W1 to 2 plus W3 to 4, and its sum can be written in terms of pressure and volume, and its sum can be written in terms of pressure ratios and compression ratios, and which is this equation over here. And the next step, what you try to do is calculate the actual swept volume, which gives you your P mean effective pressure as work done by work swept. I'm sorry, volume swept. So because you have to calculate your swept volume to get the exact answer for your P mean effective pressure. You try to include your swept volume in terms of V1, V2, V3, and V4, which is how you get this equation over here. And obviously, to sum up, it's just math over here. I'm just trying to walk you through how you actually calculate it. You get your final equation as P mean effective pressure in terms of compression ratios, in terms of pressure ratios, in terms of the initial pressure. So that's it. I hope you have understood how we actually calculate thermal efficiency and the mean effective pressure during our Otto cycle. To sum up, I'd like to thank our Professor Dr. Rajkumar Singh for providing us this opportunity to explain one of the topics that we have understood in our own way, and also to try to encourage us to be better at presenting things, which is a quite important soft skill that we ought to learn as engineers, but isn't quite taught in the curriculum. So, thank you, sir.